Hi, welcome to video 3.4a, concavity and points of inflection. So, there are two things going on in this section, the concavity and points of inflection, and then video 3.4b will be on a thing called the second derivative test, which is not to determine points of inflection, but which is to determine relative extrema, just like the first derivative test. So we're going to start with concavity. So a graph can be concave up, or a portion of a graph can be concave up, like a smile, or concave down. And finding out where a graph is concave up or down will allow you to determine these things called points of inflection. And then, of course, this 3.4b will be the second derivative test. Both of these will use the second derivative. Okay, so if you look at concave up, for example, you'll notice that if you look at the slopes from left to right, so here the slope I'm approximating is -2, -1, 0, 1, 2. As I move from left to right, you can see that the f prime of x is increasing. So what happens is if f prime of x is increasing, that means its derivative must be positive. This is the same thing as saying when f is increasing, f prime is positive. So when f prime is increasing, f double prime is positive, etc. If f double prime is increasing, then f triple prime would be positive. Therefore, the conclusion that we make is whenever the second derivative is positive, the graph of f of x is concave up. Similarly, with concave down, you can look at the slopes. Now the slopes are getting smaller and smaller, which means the first derivatives are decreasing. Hence, the second derivative must be negative. So when a graph is concave down, its second derivative is negative. And conversely, if the second derivative is negative somewhere, then the original function must be concave down there. Okay, so second derivative positive, graph is concave up. Second derivative negative, graph is concave down. Now, positive and negative mean greater than 0 and less than 0, which means we're going to find out where it's 0. Now, to determine the intervals on which a function is concave up or concave down. And at first, in the homework, you're going to see, if we look at it here, and that's what it's going to say in numbers 5 through 18, all they want to know is the open intervals on which the graph is concave up or concave down. They are not interested in where the graph has relative extrema, okay? So if they don't ask about relative extrema, do not go out of your way to find them. Eventually, we'll be asked to graph these functions, and of course, then you will need to know the relative extrema. Okay. So what you're going to do is same thing you do to find the relative extrema. You're going to start by finding the domain of the function and the vertical asymptotes of that function. And then you're going to go straight to finding the second derivative. And then you're going to determine when the second derivative, which is kind of the critical numbers of the first derivative, and I'm going to call them crucial numbers. This is not an official term, crucial numbers. It's actually something another teacher invented at another school, but I like it. So the crucial numbers are what make the second derivative 0 or undefined. Another name for crucial numbers would be possible points of inflection. But again, like critical numbers, they have to be in the domain. Then what you're going to do at that point is you're going to place these possible points of inflection or crucial numbers and your vertical asymptotes, just like before, on a labeled number line, and you're going to do the pick and plug, and you're that way going to be able to determine when f is concave up or down, i.e. when the second derivative is positive, f is concave up. When the second derivative of f is negative, f is concave down. So for example, let's say we ended up with these two numbers. I don't know if they're both crucial numbers, or maybe one's a crucial number and one's a vertical asymptote. But if you determine that the second derivative is positive, negative, positive, then that means that the original function f is concave up, concave down, concave up. Okay, so the first set of exercises, as you can see here in numbers 1 through 4, all it asks you is to state the signs of f prime and f double prime on the interval from 0 to 2, and this is the graph of f that you're looking at. So what we have, for example, here, you can tell on number, I don't know which one this is, but for example here, you can tell that the f is decreasing, hence the first derivative is negative. You can also see visually that the graph is concave up, which means the second derivative is positive. Now, in 5 through 18, as we said, they're going to ask you for the open intervals on which the graph is concave up or concave down. In this case, the graph is not given, and you are not asked to graph the function. Do not start graphing. Determine the required intervals analytically. So they have y equals, I'm going to say let f of x equals, the domain is all real numbers, there's no vertical asymptotes because it's a polynomial function. There's the first derivative, there's the second derivative. I'm going to factor it. You don't have to, but it'll make it easier for the pick and plug. It never doesn't exist. It equals 0 when x equals 1, so we put 1 on a number line. Don't forget to label, Mabel. And we're going to pick a number on the left side of 1 like 0. We'll get a positive answer because that exponent is odd, which is why I factored it to see that the signs alternate. And then, therefore, f is concave up and then concave down. So your conclusion is f is concave up on the interval from negative infinity to 1. F is concave down on the interval from 1 to infinity. Okay, so now the definition of a point of inflection. If C, and I can actually let you look at the real version in the book. Point of inflection. If CF of C is a point of inflection of the graph of f, then either the second derivative at c equals 0 or the second derivative at c does not exist at all. Now, this is kind of an interesting definition because it's saying if it's a point of inflection, then that is true. Now, I'm not saying that's false, but there is more to it than that, okay? So what happens, this is their definition. Now, there also has to be a change in concavity on either side of that number. And also, there has to be a tangent line at that point if it's going to be a point of inflection. Therefore, it cannot be a sharp turn. Because, for example, here's a sharp turn. Notice the graph is concave up on the left, but concave down on the right. And it's certainly not a point of inflection. It's a relative max. So the reason that this is not a point of inflection, even though there's a change in concavity, is that there is no tangent line there. Because remember, the derivative from the left doesn't equal the derivative from the right, so the derivative does not exist there, which means there is no tangent line there. Okay, here's a case where there is a tangent line, albeit it's a vertical tangent line, but the graph does change concave up to concave down, and there's a tangent line there, so it is a point of inflection. Okay. So even though the first derivative doesn't exist at that point, because the function is not differentiable there, because the derivative doesn't exist, there still is a vertical tangent line there. Let's pretend we have a function whose domain is everything except -1. It has a vertical asymptote at x equals -1. And let's pretend that when we solve the equation second derivative equals 0, we got possible points of inflection or crucial numbers of -3, 3, and 5. So we put that all in a number line. There's our -3, 3, and 5 crucial numbers. There's our vertical asymptote. I'd write that underneath that right away. And let's pretend that when we plugged in numbers in each of these areas, we got positive, negative, negative, positive, positive, okay, for the second derivative. So therefore, the graph is concave up, concave down, concave down, concave up, concave up. So here we have an actual point of inflection at the point -3, comma f of -3. There is no point of inflection here because we have a vertical asymptote here. Here also you'll notice we do not have a point of inflection because there's no change in concavity on either side of 5. But we do have a change in concavity on either side of 3, so that is a point of inflection. Okay, so a point on a function is either going to be a relative min, a relative max, a point of inflection, or it's simply not going to be any one of these. 19 through 36. What's interesting about 19 through 36 is, I think, in my opinion, they're asking the question in reverse order. They say find the points of inflection and then discuss the concavity of the graph of the function. Well, how the heck are you going to find the points of inflection if you don't first find out where the graph is concave up and concave down? So I would like you to think of it as do the second part first, and you will end with the first part, which is the points of inflection. Okay, so here's the original. Here's number 24. Here's f of x, domain all real numbers, no vertical asymptotes. Here's the first derivative. Here's the second derivative. Notice it never equals 0. It does equal 0 at 0, so we have one possible point of inflection. But when we do the second derivative, because this is 24 times x squared, it'll always be positive, and you'll notice there is no point of inflection because there's no change in concavity. As it turns out, even though they didn't ask, just so you'll understand what is going on, is that if you were to take the first derivative and ask for the relative extrema, you would have a relative min at 1 by doing the critical numbers. And as it turns out, this is what the graph looks like. So it turns out, sure enough, that this graph is concave up the entire time. Okay? Just as an example, f of x equals x to the fourth, f prime equals 4x cubed, and therefore you have a critical number of 0. You have a relative min at 0, 0. If you look at the second derivative, which is 12x squared, you get a crucial number of 0, and you find out the graph is concave up on both sides. This is like number 27. This is x times x plus 1 to the half. Domain, of course, the radicand, because that's an even root, has to be positive, so x has to be greater than or equal to 1, which means we'll have a number ray, not a number line. There are no vertical asymptotes. There are no denominators. So you do a product rule, okay? Rewrite this negative exponent as a positive exponent. Now get a single fraction. Find a common denominator and simplify the numerator. When you multiply these two, that you get x plus 1. Multiply through here by the 2, and you'll end up with 3x plus 2 over 2 times the square root of x plus 1. Now it comes time to find the second derivative. These can take a long time. So again, you're going to have the square of the denominator times derivative of numerator minus numerator times derivative of denominator, and then you'll simplify all that. In this case, I factored out an x plus 1 to the negative a half. This is all algebra 2. I'm going to go through quickly. You end up with this as your second derivative, single simplified factored fraction. You can tell that this fraction is 0 when the numerator is 0, which is when x equals negative 4/3. But keep in mind, our domain is x is greater than or equal to negative 1, so we cannot keep negative 4/3. When is this fraction undefined? When the denominator is 0, which is when x equals negative 1. So this is the square root of x plus 1 cubed. So x plus 1 would have to be negative or 0 in order for this not to exist, which means x would have to be negative, less than or equal to negative 1, and of those numbers, the only one in our domain is negative 1. As it turns out, you really don't have any crucial numbers because the negative 1 is the end point of our graph. So we do still plug it in and find out that if you plug in anything bigger than negative 1 into the second derivative, you'll get a positive, and therefore you know the graph is concave up the whole time, but it certainly does not have any points of inflection. So it's just a kind of review here: concave up, concave down, concave up, points of inflection, and that's the end of video 3.4a.